another type of service known as the load balancer type. So we have seen the node port service that helps us make an external facing application available on a port on the worker nodes. So let's turn our focus to the front-end applications, which are the voting app and the result app. Now we know that these pods are hosted on the worker nodes in a cluster. So let's say we have a 4-node cluster. And to make the applications accessible to external users, we create the services of type node port. Now, the services with type node port help in receiving traffic on the ports on the nodes and routing the traffic to the respective pods. But what URL would you give your end users to access the applications? You could access any of these two applications using IP of any of the nodes and the high port the service is exposed on. So that would be 4 IP and port combinations for the voting app and 4 IP and port combination for the result app. So note that even if your pods are only hosted on 2 of the nodes, they will still be accessible on the IPs of all the nodes in the cluster. Say the pods for the voting app are only deployed on the nodes with IP 70 and 71, they would still be accessible on the ports of all the nodes in the cluster. So that's how a service is configured. So you would share these URLs to your users to access the application. But that's not what the end users want. They need a single URL like example votingapp.com or the example resultapp.com to access the application. So how do you achieve that? Now, one way to achieve this is to create a new VM for load balancer purpose and install and configure a suitable load balancer on it, like HA proxy or Nginx, etc. Then configure the load balancer to route traffic to the underlying nodes. Now, setting all of that external load balancing and then maintaining and managing that can be a tedious task. However, if we were on a supported cloud platform like Google Cloud or AWS or Azure, I could leverage the native load balancer of that cloud platform. Kubernetes has support for integrating with the native load balancers of certain cloud providers and configuring that for us. So all you need to do is set the service type for the front-end services to load balancer instead of node port. Now remember that this only works with supported cloud platforms. So GCP, AWS, and Azure are definitely supported. So if you set the type of service to load balancer in an unsupported environment like VirtualBox or any other environments, then it would have the same effect as setting it to node port, where the services are exposed on a high-end port on the nodes. It just won't do any kind of external load balancer configuration, right? So later on, when we walk through the demos of deploying our application on cloud platforms, we will see this in action, right? So that's it for now. I will see you in the next lecture. Hello, and welcome to this lecture. In this lecture, we will discuss about namespaces in Kubernetes. Let us begin with an analogy. There are 2 boys named Mark. To differentiate them from each other, we call them by their last names, Smith and Williams. They come from different houses. Of course, the Smiths and the Williams. There are other members in the house. The individuals within a house address each other simply by their first names. For example, the father addresses Mark simply as Mark. However, if the father wishes to address the Mark in the other house, he would use the full name. Someone outside of these houses would also use the full name to refer to the boys or anyone within these houses. Each of these houses have their own set of rules that defines who does what. Each of these houses have their own set of resources that they can consume. Now, let's get back to Kubernetes. These houses correspond to namespaces in Kubernetes. So far in this course, we've created objects such as pods, deployments, and services in our cluster. Whatever we have been doing within a namespace. We were inside a house all this while. This namespace is known as the default namespace, and it is created automatically by Kubernetes when the cluster is first set up. Kubernetes creates a set of pods and services for its internal purpose, such as those required by the networking solution, the DNS service, etc. To isolate these from the user and to prevent you from accidentally deleting or modifying these services, Kubernetes creates them under another namespace created at cluster startup named kube-system. A third namespace created by Kubernetes automatically is called kube-public. This is where resources that should be made available to all users are created. If your environment is small or you're learning and playing around with a small cluster, you shouldn't really have to worry about namespaces. You could continue to work in the default namespace. However, as and when you grow and use a Kubernetes cluster for enterprise or production purposes, you may want to consider the use of namespaces. You can create your own namespaces as well. For example, if you wanted to use the same cluster for both dev and production environment, but at the same time isolate the resources between them, you can create a different namespace for each of them. That way, while working in the dev environment, you don't accidentally modify resources in production. Each of these namespaces can have its own set of policies that define who can do what. You can also assign quota of resources to each of these namespaces. That way, each namespace is guaranteed a certain amount and does not use more than its allowed limit. Going back to the default namespace that we have been working on, just like how the members within a house refer to each other by their first names, the resources within a namespace can refer to each other simply by their names. In this case, the web app pod can reach the DB service simply using the hostname DB service. If required, the web app pod can reach a service in another namespace as well. For this, you must append the name of the namespace to the name of the service. For example, for the web pod in the default namespace to connect to the database in the dev environment or namespace, use the service name.namespace.svc.cluster.local format. That would be dbservice.dev.svc.cluster.local. You're able to do this because when the service is created, a DNS entry is added automatically in this format. Looking closely at the DNS name of the service, the last part, cluster.local, is the default domain name of the Kubernetes cluster. SVC is the subdomain for service, followed by the namespace and then the name of the service itself. Let us now look at some of the operational aspects of namespaces. Let us start with the kube control commands. For example, this command is used to list all the pods, but it only lists the pods in the default namespace. To list pods in another namespace, use the namespace option in the command along with the name of the namespace, in this case, kube-system. Here I have a pod definition file. When you create a pod using this file, the pod is created in the default namespace. To create the pod in another namespace, use the namespace option. If you want to make sure that this pod gets created in the dev environment all the time, even if you don't specify the namespace in the command line, you can move the namespace definition into the pod definition file, like this under the metadata section. This is a good way to ensure your resources are always created in the same namespace. So how do you create a new namespace? Like any other object, use a namespace definition file. The API version is v1, kind is namespace, and under metadata, specify the name. In this case, dev. Run the kube control create command to create the namespace. Another way to create a namespace is by simply running the command kubectl create namespace followed by the name of the namespace. Now, say we are working in 3 namespaces. As we discussed before, by default, we are in the default namespace, which is why we can see the resources inside the default namespace using the kubectl getPods command. And to view those in the dev namespace, we have to use the namespace option. But what if we want to switch to the dev namespace permanently, so that we don't have to specify the namespace option anymore? Well, in that case, use the kubectl config command to set the namespace in the current context to dev. You can then simply run the kubectl getPods command without the namespace option to list pods in the dev environment. But you will need to specify the option for other environments such as default or prod. Similarly, you can switch to the prod namespace the same way. Finally, to view pods in all namespaces, use the All Namespaces option in the command. This will list all the pods in all of the namespaces. Taking a closer look at the command, this command first identifies the current context and then sets the namespace to the desired one for that current context. Well, contexts are used to manage multiple clusters and multiple environments from the same management system. It is a totally separate topic to discuss and requires its own lecture, so we will discuss contexts in another lecture. To limit resources in a namespace, create a resource quota. To create one, start with a definition file for resource quota, specify the namespace for which you want to create the quota, and then under spec provide your limits, such as 10 pods, 10 CPU units, 10 GB of memory, etc. Well, that's it for this lecture. Head over to the coding exercises section and practice working with namespaces. And I will see you in the next lecture. In this lecture, we will discuss about imperative and declarative approaches in Kubernetes. Towards the end of this lecture, we will talk about some tips that you can use in the exam. So far, we have seen different ways of creating and managing objects in Kubernetes. We created objects directly by running commands as well as using object configuration files. Now, in the infrastructure as code world, there are different approaches in managing the infrastructure, and they are classified into imperative and declarative approaches. Let's understand these with an analogy. Let's say you want to visit a friend's house located at Street B. Now, in the past, you would hire a taxi and give step-by-step instructions to the driver on how to reach the destination, like take right to Street B, then take left to go to Street C, and then take another left and then right to go to Street D and stop at the house. Specifying what to do and how to do, more importantly, is the imperative approach. On the other hand, today, when you book a cab, say through Uber, you just specify the final destination, like drive to Tom's house. And this is the declarative approach. In this case, we're not giving step-by-step instructions. Instead, we're just specifying the final destination. We're declaring the final destination. And the system figures out the right path to reach the destination. Specifying what to do, not how to do, is the declarative approach. So, what's that got to do with what we are learning? In the infrastructure as code world, an example of an imperative approach of provisioning infrastructure would be a set of instructions written step by step, such as provisioning a VM named a web server, installing the Nginx software on it, editing configuration file to use port 8080, and setting the path to web files, downloading source code of repositories from Git, and finally starting the Nginx server. So here, we're saying what is required and also how to get things done. In the declarative approach, we declare our requirements. For instance, all we say is that we need a VM by the name web server with the Nginx software on it, with the port set to 8080 and the path to the web files defined, and where the source code of the application is stored. And everything that's needed to be done to get this infrastructure in place is done by the system or the software. You don't have to provide step-by-step instructions. Orchestration tools like Ansible, Puppet, or Chef, or Terraform fall into this category. In the imperative approach, what happens if the first time only half of the steps were executed? What happens if you provide the same set of instructions again to complete the remaining steps? To handle such situations, there will be many additional steps involved, such as checks to see if something already exists and taking an action based on the results of that check. For instance, while provisioning a VM, what would happen if a VM by the name web server already exists? The same goes with creating a database or importing data. Should it fail or should it continue since the VM is already there? What if we decide to upgrade the version of software to say Nginx 1.18 in the future? It should be as simple as updating the version of Nginx in the configuration file, and the system should take care of the rest. Ideally, the system should be intelligent enough to know what has already been done and apply the necessary changes only. That's the declarative way of doing things. In the Kubernetes world, the imperative way of managing infrastructure is using commands like the kubectl run command to create a pod, the kubectl create deployment command to create a deployment, the kubectl expose command to create a service to expose a deployment, and the kubectl edit command may be used to edit an existing object. For scaling a deployment or replica set, use the kubectl scale command, and updating the image on a deployment, we use the kubectl set image command. Now, we have also used object configuration files to manage objects, such as creating an object using the kubectl create -f command with the F option to specify the object configuration file, and editing an object using the kubectl replace command, and deleting an object using the kubectl delete command. All of these are imperative approaches to managing objects in Kubernetes. We're saying exactly how to bring the infrastructure to our needs by creating, updating, or deleting objects. The declarative approach would be to create a set of files that defines the expected state of the applications and services on a Kubernetes cluster, and with a single kubectl apply command, Kubernetes should be able to read the configuration files and decide by itself what needs to be done to bring the infrastructure to the expected state. So in the declarative approach, you will run the kubectl apply command for creating, updating, or deleting an object. The apply command will look at the existing configuration and figure out what changes need to be made to the system. So let's look at these in a bit more detail. Now, within the imperative approach, there are two ways. The first is using imperative commands, such as the run, create, or expose commands to create new objects, and the edit, scale, and set commands to update existing objects. Now, these commands help in quickly creating or modifying objects, as we don't have to deal with YAML files, and these are helpful during the certification exams. However, they are limited in functionality and will require forming long and complex commands for advanced use cases, such as creating a multi-container pod or deployment. Secondly, these commands are run once and forgotten. They are only available in the session history of the user who ran these commands. So it's hard for another person to figure out how these objects were created. So it is hard to keep track of. And so it's difficult to work with these commands in large or complex environments. And that's where managing objects with the object configuration files can help. Creating object definition files or configuration files, or manifest files as it's also called, can help us write down exactly what we need the object to look like in a YAML format and use the kubectl create command to create the object. We now have the YAML file with us always, and it can be saved in a code repository like Git. We can put together a change review and approval process around these files so that a change made is reviewed and approved before it is applied to a production environment. In the future, if a change is to be made, for instance, editing the image name to another version, There are different ways to go about it. One way is to use the kubectl edit command and specify the object name. So when this command is run, it opens a YAML definition file similar to the one you used to create the object, but with some additional fields, such as the status fields that you see here, which are used to store the status of the pod. This is not the file you used to create the object. This is a similar pod definition file within the Kubernetes memory. You can make changes to this file and save and quit, and those changes will be applied to the live object. However, note that there is a difference between the live object and the definition file that you have locally. The change you made using the kubectl edit command is not really recorded anywhere. After the change is applied, you're only left with your local definition file, which in fact has the old image name in it. In the future, say you or a teammate decide to make a change to this object, unaware that a change was made using the kubectl edit command. When the new change is applied, the previous change to the image is lost. So you can use the kubectl edit command if you are making a change and you're sure that you're not going to rely on the object configuration file in the future. But a better approach to that is to first edit the local version of the object configuration file with the required changes. That is by updating the image name here, and then running the kubectl replace command to update the object. This way, going forward, the changes made are recorded and can be tracked as part of the change review process. So at times, you may want to completely delete and recreate objects. In such cases, you may run the same command, but with the force option, like this. Now, this is still the imperative approach, because you're still instructing Kubernetes how to create or update these objects. First, you run the kubectl create command to create the object, and then you run the replace command to replace the object, or delete command to delete the object. And what if you run the create command if the object already exists? Well, then it would fail with an error that says the pod already exists. When you update an object, you should always make sure that the object exists first before running the replace command. If an object does not exist, the replace command fails with an error message. So the imperative approach is very taxing for you as an administrator, as you must always be aware of the current configurations and perform checks to make sure that things are in place before making a change. The declarative approach is where you use the same object configuration files that we've been working on, but instead of the create or replace commands, we use the kubectl apply command to manage objects. The kubectl apply command is intelligent enough to create an object if it doesn't already exist. If there are multiple object configuration files, as you would usually, then you may specify a directory as the path instead of a single file. That way, all the objects are created at once. Now, when changes are to be made, we simply update the object configuration file and run the kubectl apply command again. And this time, it knows that the object exists, and so it only updates the object with the new changes. So it never really throws an error that says the object already exists or the updates cannot be applied. It will always figure out the right approach to updating the object. So going forward, any changes made on the application, whether they are updating images or fields of existing configuration files or adding new configuration files altogether for new objects, all we do is simply update our local directory with the changes, and then the kubectl apply command takes care of the rest. So we will discuss more about how the kubectl apply command works exactly in the backend in the next lecture. For now, let me give you some tips as part of the exam. So from an exam perspective, you could use the imperative approach to save time as much as possible. For example, if the question is to just create a pod or a deployment with a given image, then one of these imperative commands can help you achieve that quickly. So it's important to practice the imperative commands. If you need to edit a property of an existing object, then using the kubectl edit command may be the quickest way, right? If you have a complex requirement, for example, that requires multiple containers, environment variables, commands, init containers, etc., then using an object configuration file to create the object would be preferred. This way, if you see that you made a mistake, you can easily update the file and apply it again. And using the kubectl apply command in that case would be a better option. So for more details on the different approaches to managing a Kubernetes cluster, get yourself familiarized with the Kubernetes documentation pages. And in the upcoming lab exercises, try to use imperative approach in solving questions. Well, I will see you in the next lecture. In this lecture, we will understand more about how the kubectl apply command works. In the previous lecture, we saw how a kubectl apply command can be used to manage objects in a declarative way. In this lecture, we will see a bit more about how the command works internally. The apply command takes into consideration the local configuration file, the live object definition on Kubernetes, and the last applied configuration before making a decision on what changes are to be made. So when you run the apply command, if the object does not already exist, the object is created. When the object is created, an object configuration similar to what we created locally is created within Kubernetes, but with additional fields to store status of the object. This is the live configuration of the object on the Kubernetes cluster. This is how Kubernetes internally stores information about an object, no matter what approach you use to create the object. But when you use the kubectl apply command to create an object, it does something a bit more. The YAML version of the local object configuration file we wrote is converted to a JSON format, and it is then stored as the last applied configuration. Going forward, for any updates to the object, all the three are compared to identify what changes are to be made on the live object. For example, say when the Nginx image is updated to 1.19 in our local file, and we run the kubectl apply command, this value is compared with the value in the live configuration. And if there is a difference, the live configuration is updated with the new value. After any change, the last applied JSON format is always updated to the latest so that it's always up to date. So why do we then really need the last applied configuration, right? So if a field was deleted, say for example, the type label was deleted, and now when we run the kubectl apply command, we see that the last applied configuration had a label, but it's not present in the local configuration. This means that the field needs to be removed from the live configuration. So if a field was present in the live configuration and not present in the local or the last applied configuration, then it will be left as is. But if a field is missing from the local file and it is present in the last applied configuration, so that means that in the previous step, or whenever the last time we ran the kubectl apply command, that particular field was there and it is now being removed. So the last applied configuration helps us figure out what fields have been removed from the local file, right? So that field is then removed from the live configuration. What we just discussed is available for your reference in detail in the Kubernetes document pages. So follow this link to view that. Okay, so we saw the three sets of files, and we know that the local file is what's stored on our local system. The live object configuration is in the Kubernetes memory. But where is this JSON file that has the last applied configuration stored? Well, it's stored on the live object configuration on the Kubernetes cluster itself as an annotation named last applied configuration. So remember that this is only done when you use the apply command. The kubectl create or replace commands do not store the last applied configuration like this. So you must bear in mind not to mix the imperative and declarative approaches while managing the Kubernetes objects. So once you use the apply command, going forward, whenever a change is made, the apply command compares all three sections: the local pod definition file, the live object configuration, and the last applied configuration stored within the live object configuration file, for deciding what changes are to be made to the live configuration, similar to what we saw in the previous slide. Well, that's it for this lecture. I will see you in the next. Hey, so here is a quick reminder, and I hope you don't mind me jumping in like this. I wanted to take